Imagine a scenario so extreme that it challenges our understanding of scale and physics. Today, we delve into a wild thought experiment. What if we poured all of Earth's water onto the sun? At first glance, it might seem like a recipe for disaster, yet this idea invites us to explore the vast differences between our home planet and the colossal star that sustains life on Earth. In this video, we will examine the hypothetical impact of adding our planet's water, a substance we cherish for life, into the intense, fiery furnace of the sun. We will break down the physics behind such an event, explore the immediate and long-term effects on solar activity, and ultimately gain a new perspective on the enormous scales at play in our solar system. Join us as we journey into this fascinating collision of the terrestrial and the celestial. Prepare to be truly amazed by science. Consider the sheer scale of the two celestial bodies involved. Earth, a blue marble abundant with water, holds approximately 1.386 billion cubic kilometers of water in its oceans, lakes, and rivers. In stark contrast, the Sun, a massive ball of incandescent plasma, contains an unimaginable mass and volume. When we compare the volume of Earth's water to the size of the Sun, the differences become astronomical. The Sun's diameter stretches nearly 4 million kilometers, and its mass exceeds that of Earth by more than 330,000 times. Pouring all of Earth's water onto the Sun would introduce a minuscule amount relative to the Sun's overwhelming mass and energy output. Despite the dramatic imagery this scenario evokes, the reality is that Earth's water would likely vaporize and disperse instantly in the Sun's extreme temperatures. Yet this thought experiment helps us appreciate not only the power of our star, but also the delicate balance that allows water to persist on our planet. The contrast between the finite resources of Earth and the boundless energy of the Sun highlights the fragile nature of our environment and the forces at work in the universe. This stark numerical comparison deepens our cosmic understanding beyond measure indeed. When water meets the extreme conditions of the Sun, physics takes on a spectacular display. At temperatures exceeding 5,500 degrees Celsius on the surface and reaching millions in the core, any water introduced would instantaneously convert into plasma. The moment droplets approach the solar atmosphere, they are torn apart by immense gravitational and electromagnetic forces. Molecules disintegrate into their constituent hydrogen and oxygen atoms, which in turn are stripped of their electrons. This rapid ionization process adds a negligible amount of additional hydrogen to the Sun's already vast nuclear fuel supply. Furthermore, the energy released from such a transformation is minuscule compared to the Sun's ongoing fusion reactions. The dynamic interplay of intense radiation, magnetic fields, and thermal pressures would quickly absorb and dissipate the water's material. In essence, the water would not create a visible disruption, but instead blend seamlessly into the solar plasma. This thought experiment illustrates the robustness of stellar environments and the insignificance of terrestrial resources when confronted with the scale of a star's energy and mass. Ultimately, this scenario emphasizes that even an entire planet's water is but a drop in the cosmic ocean compared to the overwhelming forces at work within a star indeed. The introduction of Earth's water into the Sun would trigger an immediate, though transient, set of phenomena on the solar surface. As water vapor encounters the searing heat, it disintegrates in an instant, producing a fleeting burst of steam and ionized gas. However, the sheer intensity of the solar environment would overwhelm these minor disturbances. Localized cooling might occur momentarily in tiny pockets where water is injected, but the vast thermal energy of the Sun would rapidly restore equilibrium. Furthermore, the high-energy particles from the disintegrated water would become integrated into the existing solar plasma without altering the Sun's overall behavior. Magnetic fields might briefly interact with the new particles, but any resulting fluctuations would be negligible when compared to the Sun's continuous and powerful magnetic dynamics. In this immediate aftermath, No significant solar flare or coronal mass ejection would be expected solely from the water's addition. Instead, the incident would simply blend into the ongoing turbulent convection processes, demonstrating once again the immensity and resilience of our star's natural forces. Ultimately, any initial disruption fades as the sun's inherent stability reasserts control, proving that even dramatic inputs are insignificant against its colossal power, a testament to solar supremacy indeed. Over the long term, adding Earth's water to the sun would have virtually no lasting impact on its overall activity. The minuscule infusion of additional hydrogen and oxygen would be rapidly assimilated into the star's continuous fusion cycle. Given the sun's immense mass and the scale of nuclear reactions occurring every second, the extra material is effectively diluted. Solar models indicate that such a negligible perturbation would not alter the balance between gravitational forces and the outward pressure generated by fusion. Moreover, the dynamic processes that govern sunspots, solar flares, and coronal mass ejections operate on scales far beyond the influence of any terrestrial addition. In essence, while the theoretical injection of water might momentarily affect local regions, it would not trigger a cascade of changes or destabilize the solar structure. The sun's self-regulating mechanisms ensure that its energy output remains consistent over billions of years. This thought experiment reinforces the notion that Earth's resources, however precious to us, pale in comparison to the vast energies at work in stellar cores. In the grand scheme of cosmic evolution, the sun remains impervious to such minor contributions, reaffirming its dominant role in our solar system's intricate balance beyond any doubt indeed. This extraordinary thought experiment serves as a reminder of the colossal differences between Earth and the sun. When we imagine pouring all of Earth's water onto our star, we confront the reality that even our planet's most abundant resource is minuscule in comparison. The sun's unfathomable energy production, driven by relentless nuclear fusion, dwarfs any conceivable terrestrial addition. This exercise in scale not only highlights the robustness of stellar processes, but also deepens our appreciation for the delicate conditions that allow life to flourish on Earth. By contemplating such extremes, we gain insight into the vastness of the cosmos and the inherent limitations of our planetary resources. It encourages us to consider our place in the universe and to cherish the fragile balance that sustains our environment. Ultimately, this scenario exemplifies the interplay between the finite and the infinite, prompting us to explore further the mysteries of space and the marvels of our solar system. This mental exercise not only stretches our imagination, but also underscores the awe-inspiring magnitude of stellar phenomena. It invites scientists and dreamers alike to ponder the wonders of the universe and the delicate scales that govern celestial mechanics. A reminder of nature's eternal mystery indeed. One crucial aspect of our scenario is that water contains hydrogen, the primary fuel of the sun. The sun undergoes nuclear fusion by converting hydrogen atoms into helium, releasing an immense amount of energy in the process. At first glance, adding Earth's water, which contains hydrogen, might seem like it could enhance this process. However, the quantity of hydrogen in Earth's water is trivial compared to the sun's reserves. The sun already burns about 600 million tons of hydrogen per second, meaning Earth's entire water supply would provide only a momentary increase. Even if we could somehow efficiently inject this hydrogen into the sun's core, it would barely make a dent in its 10 billion year lifespan. This underscores the vast differences in scale between planetary and stellar processes and demonstrates how even massive earthly quantities are minuscule in an astrophysical context. A common misconception is that dumping a massive amount of water onto the sun might somehow put out the fire, as if the sun were a giant campfire. However, the sun doesn't burn through combustion, it undergoes nuclear fusion, an entirely different process that doesn't require oxygen. Instead of extinguishing the sun, adding water would merely introduce more fuel in the form of hydrogen. This would momentarily increase available fusion material, though in an amount too small to have any meaningful effect. Unlike a fire, which depends on oxygen to sustain its flames, the sun's energy comes from crushing gravitational forces that squeeze hydrogen atoms together, fusing them into helium. The presence of water would be irrelevant to this process. It would just break apart into its atomic components and be assimilated into the existing fusion cycle. While hydrogen in the water would contribute, even insignificantly, to the sun's fusion, what about the oxygen? Oxygen is a much heavier element than hydrogen, and it doesn't play a role in standard hydrogen fusion reactions. Instead, any free oxygen atoms would likely get absorbed into the sun's upper layers and become part of the plasma mixture. Over time, these atoms would settle into the sun's convection currents, but would not significantly alter its chemical composition. Some might argue that adding a significant amount of oxygen could trigger new fusion reactions, such as those occurring in heavier stars, but the sun simply isn't massive enough for that. Heavier elements only fuse in larger stars near the ends of their lives, meaning Earth's water would have virtually no long-term effect on the sun's life cycle. For a star, color and brightness depend on temperature and composition. The sun's surface temperature is about 5,500 C, 9,932 Fe, and it emits light primarily in the yellow-white spectrum. If Earth's water were added, it wouldn't significantly alter the sun's overall temperature or structure. The sheer energy output would remain the same, meaning it would still shine with the same brightness. However, in the immediate aftermath of introducing water, there might be small, localized effects in the form of intense bursts of energy as water molecules are torn apart and ionized. These could create temporary bright spots or minor solar storms, but overall, the sun would continue shining as usual, unaffected by the new material. If Earth's water were somehow transported toward the sun in its liquid form, the moment it encountered the outermost layers of the sun, it would instantly turn into steam. But in the vacuum of space, steam behaves differently than it does on Earth. Instead of forming clouds, the superheated water molecules would disperse rapidly into individual particles, becoming part of the solar wind, a stream of charged particles constantly emitted by the sun. This means there wouldn't be a dramatic boiling effect like a giant pot of water on a stove. Instead, the water would simply vaporize and dissipate almost instantly into the surrounding plasma, blending into the sun's already complex and energetic outer atmosphere. Now, let's consider what would happen if we could somehow teleport all of Earth's water into the sun in an instant. The sudden introduction of such a large mass might create a momentary disturbance in the sun's outer layers, potentially triggering small-scale shockwaves. However, these effects would be incredibly brief. The sun's immense gravitational forces would rapidly distribute the new material, and any disruptions would be smoothed out almost immediately. The sheer scale difference between the amount of water and the sun's mass means that even this sudden flood wouldn't significantly impact the sun's long-term behavior. A star can explode in a supernova under certain extreme conditions, such as when it has exhausted its nuclear fuel or has accumulated too much mass in a short period. However, the sun is not a candidate for a supernova. It lacks the necessary mass to undergo this dramatic fate. Adding Earth's water wouldn't provide nearly enough additional mass or fuel to trigger an explosion. At best, the water might briefly disrupt some surface activity, but it wouldn't cause a large-scale detonation. The sun's structure and self-regulating processes ensure that it continues its stable nuclear fusion without drastic external influence. The sun has an extremely complex and powerful magnetic field, generated by the movement of charged particles within its plasma. While adding Earth's water would introduce more particles, the amount would be insignificant compared to the sun's vast plasma currents. Any slight disturbances to the magnetic field would be quickly neutralized, and the sun's 11-year solar cycle marked by shifts in magnetic activity would remain unchanged. Solar storms occur when the sun releases bursts of energy, often in the form of coronal mass ejections or solar flares. Some might wonder if adding Earth's water could trigger an increase in these storms. While the rapid vaporization of water could create small-scale turbulence, it would not be powerful enough to trigger significant solar events. The sun already experiences much larger disturbances naturally, such as those caused by its own internal magnetic activity. What if, instead of liquid water, we introduced Earth's entire ice supply? The effect would be essentially the same. Ice would vaporize as it approached the sun, just like liquid water. However, because solid ice takes longer to convert into gas, the process might unfold over a slightly longer time span. Even so, the end result remains unchanged. The water molecules would be torn apart, and the sun would remain largely unaffected. Some might wonder if the sudden introduction of Earth's water would create a shell of vapor or steam around the sun. While the concept of a water barrier sounds interesting, the reality is that it wouldn't happen. The sun's intense heat and radiation would instantly disperse the water into space. Any steam or water vapor would be absorbed into the solar plasma and become part of the solar wind, which constantly ejects particles in all directions. The sun's powerful gravity ensures that nothing can linger around it for long unless it's part of its plasma structure. So, no, there wouldn't be a shell of water surrounding the sun, just a brief, violent vaporization before everything is absorbed into the star's existing environment. A fascinating question is whether adding Earth's water could transform the sun into a different type of star. Some stars, known as Wolf-Rayet stars, have strong stellar winds and high oxygen content, but they are much larger and older than our sun. The addition of Earth's water wouldn't provide enough material or the right conditions to trigger such a transformation. The sun's evolution follows a set path determined by its mass, and Earth's water wouldn't alter that course. The sun will still eventually become a red giant, then a white dwarf, following its natural life cycle. What if, instead of dumping all of Earth's water at once, we slowly fed the sun with water over millions of years? Even then, the impact would be negligible. The sun already loses 4 million tons of mass per second due to energy released from fusion, so even regularly adding Earth's water wouldn't make a difference in the grand scheme of things. The sun is simply too massive and too self-sustaining for such a slow, external process to alter its fate. Would dumping Earth's water onto the sun have any significant effects on the rest of the solar system? The short answer is no. The sun's mass wouldn't increase enough to affect planetary orbits, and its radiation output would remain steady. If anything, the minor temporary disturbances in the sun's outer layers might lead to slightly stronger solar winds, but this wouldn't be enough to alter planetary conditions. Earth and its neighboring planets would continue to revolve around the sun as if nothing had happened. Since hydrogen is the sun's fuel, could adding water delay its eventual demise? While hydrogen is the main ingredient for fusion, the amount added from Earth's water would be so tiny compared to the sun's total fuel supply that it wouldn't make any difference. The sun has enough hydrogen to sustain itself for another 5 billion years, and Earth's water would extend that by only a fraction of a second, if even that. In other words, it wouldn't buy us any extra time. Comets are mostly made of ice, and they frequently collide with the sun. So how would adding Earth's water compare to a massive comet impact? The answer is simple. It would be similar, but on a much larger scale. However, even the biggest comets, such as Comet Bernardinelli-Bernstein, which is over 100 kilometers wide, are insignificant compared to the sun's mass. When comets hit the sun, they evaporate instantly without causing any noticeable changes. Earth's water, while far greater in volume than any single comet, would follow the same fate. It would be consumed without any major effect. Some might wonder if adding a huge amount of mass to the sun could push it past the threshold to become a black hole. However, this is impossible. A black hole forms when a star at least 20 times more massive than the sun collapses under its own gravity. Even if we somehow added multiple Earths to the sun, it would still be nowhere near large enough to undergo this process. The sun's eventual fate is to expand into a red giant and then shrink into a white dwarf, not to collapse into a black hole. The sun rotates, but it does so slowly compared to other stars. Could adding Earth's water increase its rotational speed? In theory, if the water were delivered in a way that exerted a force, it could cause a tiny change in rotation. However, this effect would be so small that it would be practically unmeasurable. The sun is already rotating due to internal convection currents and magnetic activity, and adding water wouldn't change this process in any meaningful way. If we dumped all of Earth's water onto the sun, the bigger problem wouldn't be what happens to the sun, it would be what happens to Earth. Without water, Earth's climate would become uninhabitable. Oceans play a critical role in regulating temperature, absorbing carbon dioxide, and supporting life. If we lost all our water, the planet would become a barren desert, incapable of sustaining any known life forms. This means that even if adding water to the sun had some unexpected benefit, it wouldn't be worth sacrificing Earth's habitability. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.